Let us see. Let us start it. It's not. Yes, now it has started. All right. So I think let us start this meeting so the students can join, and because we are recording, they will be able to see this recorded video later also. All right. So we'll start with this problem. And if you see this problem, I think some students raised their hand, but do you see any missing data in this problem?
Yes, we can't find the components without the angle. I think so because I couldn't find the angles because I thought the angle was missing.
Yes, that's correct. So actually, this angle is 45 degree. Sorry, this one, the C, it is 45 degree, and at B it is 60 degree. So you have to consider that there was a missing data in this particular problem. Sorry. Copy and paste. Yeah, so this angle will be 60 degree, and this one will be 45 degree. So now can you solve this problem? So what you have to do is you have to find the axial force diagram of the member ABCD. Okay. So generally we draw the member in the horizontal, the member aligned in the horizontal direction, and then we try to draw the axial force as shown in the y-axis, and the length will be shown in the x-axis. Okay, so I'm just drawing without the cross section. If I try to just represent using this member, so we can also include the cross sections like this. So let us say these are different cross section, and this is your. Okay, so let me just not take this. Okay, I'll just draw it here because my last drawing was not good. So let us say this is your member. So now to draw the axial force diagram, you have to find the reactions as well as you have to see what is the applied loading in the axial direction. Okay, so somehow you have to convert this thing, the outer plane or the transverse component will not contribute anything to the axial force diagram. So we'll neglect or will not show the transverse. Transverse means perpendicular to the axial direction. Okay, so this is A, this is B, this point is C and D. So if you see at this point, there will be some force coming in the axial direction, and there can be in some case it can be like there is some vertical or load perpendicular direction, but because this is symmetry, you can see this component T2 sine of this angle, okay, will be cancelled by this component here. Okay, so you'll have one load coming here and another load or axial force coming here, and then you will see that at this particular point there will be some reaction this way. So I can write this is as RA and this one as, let us say, F1 and this is F2. Can you tell me what are these the values of these forces F1, F2 and RA? If you simply draw a free body diagram and try to do that, so you'll be able to find out. So you can see here this is 20 kilonewton. So this component is 20 cos 45. So and you can see from here also you'll get the same thing, 20 cos 45. So 2 into 20 cos 45 will be your this F2. So that will turn out to be 20 times 2 times 1 by root 2. So 20 root 2, which is 28.28 in kilonewton, right? And what will be F1? F1 is T2 cos 60, and from here T2 cos 60, and that will become 2 times 10 cos 60, and cos 60 is 1 by 2, so it will become 10 kilonewton. And this will be RA, then you can see sum of this two, F1 plus F2, it will be 38.28 kilonewton. Now, once we know the forces, like applied force and the reactions, then we can try to draw the axial force diagram by first drawing the axis, which is your x-axis, and this y will represent the axial force. Okay, so we'll call it AFD. Okay, so now can you tell me, like, if I take the section C and D, okay, so to find the axial force, what generally we do, we just take a cut section here and see what is like the free body of either the left side part or the right side part. If you see, the right side part or the left side part will look like this. Okay, I'm just drawing for one, then you'll understand. We'll not do this for other cases. Yeah, so this is the place where I have cut. You see that? So I'll use this axial force tensile as positive, and let us say this is my Tx, and so action and reaction will say that both sides it will be Tx and opposite. Okay, and these are your applied forces. Now if you see, it is easy to take this right side because there are no loads. You can and that gives us Tx equal to 0. The same thing we'll also obtain from this left side free body. So you have to choose like the side which you feel convenient. So either one is fine. Technically, they're no different. Okay. So that means any section, if any point if you take in this particular section, it will say that the axial force is 0. Okay, so that means it is on this line. And what about BC portion? Can you tell me now? Anybody?
Sir, 28.29 to 28.28.
28. It is positive and it is constant throughout, right? So it will be this 28 point. You can write here 28.28 kilonewton. And what will be in the section AB?
Minus
AB.
38.2.
BC it is negative.
Should be
38.28. Plus 38.28.
38.28.
So plus or minus? Still, I think that some
Plus.
students told plus, some minus. Can you
Should be
confirm?
plus.
Sir, it is
Yes, it
plus.
should be plus.
Should be plus.
Why? Because if you see, if you cut here and then take this left side portion, it is easy because you have only one force. Then I have this. No, I think.
It is minus, sir.
Minus
Yeah.
it will be.
So it is compressive force, right?
So I
Yes,
think
sir,
this.
it will be
so
compressive.
I
Then
think we
minus
have
two.
started
Yes,
making
sir.
mistake from here itself. Okay.
Yes, sir.
Yes, sir. It is
So we have
compressive
started
force.
making mistake here itself. So that's why we are leading to this mistake here also. So if you see here, if I just cut here, then if I just take this side, okay, or any side I can take. So if I take BC portion, then I have this force and then a cut section of BC here. And then you can see I'll assume Tx positive like this, and there is a force here which is 10, and there is a force here which is 38.28. So this is this side, and I can do the same thing taking this side also like this. So there is a force here 28.28. And then you can see I have Tx positive like this. So a arrow coming out from the section will be positive. Okay, so it is like trying to pull out the material from the surface. Okay, so that sense is called positive axial force. So both, if you take either this one or that one, both will say that Tx will be minus 28.28 kilonewton. So this way, this was wrong. So I have to go down and I have to draw this one here. And then you'll see that here in this portion, it will be 38 point. And you like while you are drawing this thing, you don't have to be like exact true scale picture or graphical like exact magnitude is not needed. So you have to just approximately show this one. Okay. So 28, you can see this, if this is 28, this cannot be like 10 only, right? So you can see it is not in true scale, but as a representation of this axial force diagram, it is fine because we are mentioning the important point by showing the value here. Okay, so that way it is fine. And you can see one another important point here, that this particular portion, so it is not well defined, right? Because there is a jump. So sometimes people join this as a line like this, or you can use, instead of a straight line, sometimes people use a dotted line. So at this point of time in your first year course, this is fine, no problem. But if you see in practice, there will be some stress concentration, and when at the application of this force, there will be some higher stress. And whereas you can see this corner may not be stressed much, because if I just put the load here, like stress concentration and this thing happens. And then if you try to find out the stress by finding this axial force and dividing the cross section area, so it may not be accurate. Okay, so there are some things happening, and if we do a detailed analysis using some computational code like finite element software, ANSYS, Abacus, probably bother about those things, the stress, concentration and all. So we'll treat that the axial force between these sections are fine. And at this particular C point, there is a jump, and that jump will just represent by a line. Okay. So this is it. So this is our axial force diagram. Axial force in the component. Now, if I try to see the next question. Here, you can see this problem along the axial direction. I have forces as well as in the perpendicular direction. Give you the shear force and bending moment as you have done earlier, the other tutorial sheet. And the forces along this axial direction will be okay. So here we will be only concentrating on the axial force for drawing the axial force diagram. Okay, we will not consider the perpendicular components. But if you are asked to draw the SFD and BMD, probably that time you need those forces. Okay, so then we'll just simply first write the component in the axial direction. So first draw the same component, and then you see if I try to draw, let me draw it here because I'll just represent axial forces here. So here if you try to draw the free body diagram of this is a roller support, so I'll have one vertical reaction. Let us say this point is A and this is B, and then this is BY. And then I'll have, because this is a pinned connection, so pinned connection, I'll have two reactions. A, this is Y and this is X. And you see all these forces will have both horizontal and vertical components. And this AY and BY can be obtained by considering the vertical components. Okay. But because that is like finding AY and BY will not give any information for drawing the axial force diagram, so we'll not try to do that. So what we'll do, we'll take the horizontal component of this force, and this one we don't need, so we'll find this one, and then you can see there is a horizontal component of this for this direction and this one. So but all forces will have some vertical component, but this. All right, so now if you see these forces, if you calculate using these angles, you'll I'll just show using red color here. So this one, if you just calculate, this is the point where it will lie. So it is important how you show this. So you can see if I just show like this one, like you can either think that it is acting at this point or this at this point. So better to use a single representation. So here, what I'll do, I'll just draw the forces as what I have done here. I have done like this. You can see the forces are the rear end of the arrow is indicating the point of application of the force. So that way you can show, sometimes people also use differently. So you can see this force can be also shown using this way. So it's the same force I could have drawn like this. Okay, so if you use whatever diagram you use, you probably you can give a point like this B, so that will make our life easy. Okay, so after that, either you show this way or that way, it's fine. So for this case, we'll show maybe just one arrow either here. So this way we can show. Okay, but this you can see this B point is the application of this force, because that is important, because you know when you select the sections, you need to know where it is applied. And this force will have magnitude of 14.5 kilonewton. The component of 20 kilonewton in the horizontal direction. And here I have this, sorry, this is B, so we'll take this one as C. And then this is your D point. And for this also, we'll show like this. And this point is, this force will be 40 cos 60, so it will come 20 kilonewton. And whereas here, I'll have this force, and it will be 30 cos 30 degree, so it will come around 25.98. At this point, you will not have any axial force, but this AX will come, and you can see AX will be the resultant of this thing, the sum of this thing with the sense. So it will be 14.14 plus 25.98 minus 20. So it turns out to be 20.12. Okay. All right. So this is what we need for drawing the axial force diagram. All right. So now you have to tell me. So where is the point C? Yeah, here. So this is your C point. All right. So I have shown you. Maybe I can use this color, red color dots to indicate the point of application. Yeah, now you have to tell me what are the forces in, and this is your B and this is your A. So start with right side. Like I prefer to go from the right to the left, even in the SFD and BMD case, or for this particular case also. So let us go from right to left. So I'll start with section BC. So what will be the axial force between this BC?
0.
0.
Yes. So this is 0. And then next CD?
Minus 25.98.
Minus 25.98. So it will be compressive, and this is what. And then what about this CD portion?
Minus 5.9.
5.98.
Yes, you can see if I take any one, so this side, left side or right side, you'll see that this will give like, I have to just show a TX like this, and then you can see this is your TX minus 20 plus 25 will be 0, and then TX will be minus 5.98. Okay. So that will be somewhere here. And as I told, I can join this as a line, but dotted line also is fine. Okay. So now let us, sorry, this will go up to this point. And then I have this last portion AC. Can you tell me what will be?
Minus 20.12.
Yes, so minus 20.12, you can take this side, you can see that this is TX, so TX plus this thing will be 0, so TX will be minus 20.12. And you can see this is my 25 in the negative side, so the 20 will be in between this line. This is your 5, minus 5.98. Okay, so you just show a line which is just between this, because this would be just below this line, okay, or maybe in the negative sense, you can see this 20 will be just smaller than this 25. Okay, so this is 20.12 kilonewton. This is all kilonewton. You have to just make this. Yeah, so this is your axial force diagram. All right. So it's simpler than the Benioff shear force diagram. So I think it will be very easy for you to find those axial force diagram. So here question 3. If I just take it, I think we can just discuss this very quickly. So we will be trying to draw the axial force diagram of this horizontal member. Okay, so maybe it is mentioned. Draw the axial force diagram of the horizontal part ADB. So it is not mentioned ADB in the figure. I think this point will be A and this middle point is D, and the rightmost point will be B. Okay, so this is your A point. This is D point, and this is B. All right. So what do you have to do? Can you tell me how we can proceed?
Sir, what I did was first I found out the tension in the wire, and after finding out the tension in the wire, I then replaced the tension force at the point D with a force and a couple, and then I mean the force and the couple that is being produced by that force, I replaced it at D, and after that I drew the axial force diagram.
Yeah, so that is correct. So first what we have to do is we have to take whatever load is coming to this ADB member. So ADB member will be subjected to a force at D and a couple, because you can see this is if I cut here, I'll see that there is actually a tension T, and this tension is nothing but 70 into 9.81 Newton. So then this T, because it is offset, so if I try to see what is equivalent force at D, so you know that the force transfers, it will be transferred as it is, and it will give additional moment or couple, which is R cross T, but here because it is planar, so you can see it will be just 2 times the T, okay, where this is 2 meters, so this distance into the force. But you can see this information is not required for axial force diagram, so only this one will be needed, okay, because this will anyway give some forces in AX, sorry, AY and VY. So if I try to draw it, the entire Fibonacci diagram, this is A here roller, so that's why VY, here pin, so AX and AY. Now if you see summation of Fx will give me what is this AX, okay, and AX will be like AX plus T will be 0, so AX will be minus T. All right, so T is coming to be, you know how much it is?
686.70.
Yeah, it is 686.7 Newton. So then this will be minus. So if I just consider the axial force only, and this is, you just remove all this now, you don't need. So here this is minus 6.7 Newton, and this is 6.7 Newton. Now if you see this dB portion, there is nothing, so it is 0. So if I just take this one, so this within this it is 0, so there is nothing, and here it will be tension or compression. Can you tell me this between A and D?
Tension, sir.
Yeah, it will be tension. You can see that if I take this side, you see I have shown you this
Tension
force AX, but it is negative. That means the force actually is inverse of this one. So it is acting from this to that. So that will give you Tx as tension. Okay. Or if you just go by mathematics, you will see Ax plus Tx is 0, and then Tx is minus Ax, and because Ax is negative, so this thing will become positive. And you can show this diagram by simply drawing this one. Okay, and you just mention this value here, 686.7 Newton. Okay, so this is your AFD. So these are simple. Now we have one problem which is related to the torque diagram, twisting moment. Okay, and how many of you solved this? Already have solved this one?
Yes, sir, I solved it.
Yeah. So then you have to guide me for solving here in this live session. Can you tell me how you have solved?
Sir, first I took I mean it was given that T1 is equal to 2T2 and T3 is equal to 2T4 from that, and T1 value was given. So from that I calculated the amount of torque, by which I should replace on that given beam, or that that what to say, that given rod that is given. So
Right.
from that I replaced it with it, and then also for T3, T4 also I did the same, and by you in the last video you showed that same type of problem, and then using the same concept, that the torques have to be equal and opposite. From that I calculated the moment, and then made the twisting moment diagram.
Yeah, so that's correct. So you have to first find the applied torques. So for finding applied torques, the given information we have to use. So here, if you read the statement, you will see that the circular shaft ABCD is supported over two bearings at A and D. So these are bearings here at A and D. So bearings means it allows the rotation about this shaft axis. Yeah.
Yes,
so that means the torque, resistant torque at
there
A
would be
and
no
D will be 0. Yeah.
no twisting moment at A and T.
Right.
And
Then
T1,
two.
T3 value.
Right, T1 is 2T2 and T3 also is 2T4. And you can see T1 is given. So then if T1 is given, T2 you can find out. And then you can find out the total torque acting on the shaft ABCD at this point B by taking moment about the point B. Moment means moment about the axis. So that will give you, like, you can see it is just T, because T1 is higher than T2. So it will be T1 minus T2 times the distance or the radius R. Okay, so it will be then you can see total torque is coming T1 times R, right? 2T minus, it is T2 minus R, right? So let us see that, not here. I'm using the whiteboard. So here you can see T1 is 2T2. And the torque, if I try to calculate, because T1 is higher, you can see the torque will be something like this. And this one, let us say this is TA, sorry, this is B point. So TB is equal to T1 minus T2 times R. And you can see this T1 is 2T2, so it will become T2 times R. And T1 is given 12, right? So it is 12 kilonewton. So T2 is 6 kilonewton then. So it will be 6 times the distance. You have to see what is the distance. It is
0.4 meters.
It is not given here, right? Maybe in the statement it is given.
Yes, sir.
Yeah.
The diameter was given.
Diameter is 400, so radius is, sorry, 800, so radius is 400, so 0.4 meter. Okay, so 6 into 0.4, and the 6 is in kilonewton, so it will be kilonewton meter. All right. So that means it will be 2.4 kilonewton meter. So now if you see, there are some relation given, T3 and T4, but this may not be needed for solving this problem, because you see this is TB and there is no torque at A and D. So that means the torque has to be, this TB torque has to be balanced by the torque at C, right? And you can see this will be balanced by a counter torque at TC and this counter torque TA. And you can see if I now one thing you have to show here. What is that? Can you tell me? For drawing the axial force diagram, I told you that you assume tension as positive, right?
Yes, sir.
But here you can see because the torque sense will be positive on or negative based on the coordinate system you adopt, right? So whatever coordinate system you'll adopt, based on that it will become either positive or negative. So first you have to show a coordinate system. Okay, so and the coordinate system should be right hand orthogonal coordinate system. So then you can like use your mathematical equation correctly. So let us say this is my x, and then if I just use this as y, can you tell me to make it right hand orthogonal, what should be your z direction?
Downward, sir.
Downward.
Yeah, so it is downward. So the sense right hand screw means x to y. If we try to move, then the screw should go towards the z direction. Okay, a right hand screw, if you try to move from x to y, then the screw should move along z direction. So now you can see, so what is my positive mx, so moment about x, right? So that we have to see which one is positive. So here you can see this TB, okay? So TB is shown in this using this arrow. So can you tell me whether this is positive or negative?
TB is positive, sir.
Positive, sir.
Yeah, why you say that? Because it is actually when I move right hand screw from y to z, so you can see that will move along x direction, and that is the direction. So this is actually a movement from y to z. So y to z, if you see the cross product, y cross z, that means the j cross k is positive, right? So it is the j cross k component. So that means TB is positive. So if I try to then write the equation, so this is positive and then TC is negative, so equal to 0. Okay, so this is moment about the x-axis. All right. So then I can say the TC will be equal to TB. So TC means here the magnitude, okay? Because I have used a sense here as just opposite to TB. So that's why I'm just getting that the magnitude of TC will be equal to the magnitude of TB. Okay, so then you know that this is 2.4 kilonewton meter. Now you come up for the diagram. Okay, so for drawing this twisting moment diagram, again I have to make the beam or the shaft horizontal. Okay, so this is your starting point at A, and then 2 meter apart there will be one B point, and then another 3 meter you'll have a C point, and then 2 meter apart you'll have a D point. Okay, and here I'll just show the forces. This is my TB, and this is TC. All right. So now you just tell me what should be the diagram. This is your x-axis, and y-axis should be the twisting moment. You can see that CD portion, there is nothing, right? So only torque, non-zero torque we will get between B and C. But this is 0. This is also 0. Now you have to see this one, and you can see by looking at the problem that between B and C, the torque will be constant. So that means it is a horizontal line from B to C, but only thing I have to now see whether it is positive or negative. Now you tell me what should be the sign.
Negative, sir.
Sir, it's negative.
Negative.
Yes, sir.
Negative.
Yes, so it will be negative because you can see if I just try to cut here, then I have a beam where there is, this point is B, and I have applied torque here, and this is your A point, and this is your at X, right? This is the point at X. Now I'll show this positive Tx, because this here, the positive Tx should be shown like this, and this is your TB applied torque. And you can see Tx plus TB should be 0, then the Tx for equilibrium should be negative of TB plane. Just have same magnitude, but the sense is negative. So then you can draw this diagram in this way. And this magnitude is minus 2.4 kilonewton meter. All right, so this is all about your axial force and twisting moment diagram. Now I want to emphasize a little bit on the shear force and bending moment diagram. Okay, I think Professor Jain, when I was looking at that MS team of section 1 and 2, I have seen some few attempt students are making to draw SFD or BMD similar to some letter of English alphabet, which represents the first letter of their name, right? Some people have represented P, and then some R, S, something like that. So I think it's a very interesting thing he has done, and I think some student also tried and got some very interesting curve. Okay, so that will be a nice approach for learning this concept of SFD and BMD. So I can start with a simple problem for your understanding, and then we can move forward. Yeah, go ahead.
Sir, please show that how we will check in from right side in this diagram.
Right side means what I told you. Just start looking at the beam from this side. So you choose from section C and D. Okay. So that is what my intention. So you just draw first this one and then this one, and then you draw this one. Okay. So it is in this AFD, AFD and TMD. You'll see that it will not make any difference. Okay, so whether you start from this side or that side, you look at from, you start solving this problem for this side. But I have I told you that I prefer to go from this side to that side. It will be just clear when I discuss one or two problems in SFD. Okay, shear force diagram. We'll just see that. For example, you see, let me try to draw as you are doing for this English like letters. So let me choose one letter for you. That is, let us say some M. Okay. So let us say this is maybe I'll use a different color so that it looks nice. So this is your total beam length. So this is middle of that. And then I'll draw some vertical line here and probably I'll go middle of it, straight line, and then I'll go here and then come down. So this is a representative Venn diagram which looks similar to the alphabet or letter M, right? All right, so this is, let us say, BMD. Now you have to tell me what should be the corresponding loading. Okay, which kind of loading can give you this kind of bending moment diagram. So I'll draw one line because generally SFD also is related to this problem. And then this is your beam, let us say. So you have to tell me what are the loading. This is, I'll call FBD because only I'll first ask the forces, and then you can think of like how FBD can be related to the boundary conditions. So whether this end is fixed, pinned, or roller support. So that will come later. Okay. So first let us concentrate on the FBD. Okay, the free body diagram, and here there will be the shear force diagram. Okay. So I have given you the final figure for Venn diagram, and from here you have to do some reverse engineering and come back here. So the loading of the beam. Okay. So can anybody help me to draw this loading on the beam?
So concentrated load at 3 points, I think.
Concentrated load at 3 points.
Yes, sir.
What are the points?
Sir, one should be middle and
so probably let me say this is your B, sorry, A, B, this is C, D, E. Now can you tell me what are the points?
so BCD.
BCD, okay, that's, so he says that forces on B, C, and D. And forces means these are point loads, right? Point force.
Yes, sir.
Okay. Yeah, so that's correct. But I think it is not only because I have mentioned that it is FBD. So you will see it is the forces will not be limited to B, C, D only. The A and E also will have some force. Okay. So you will see that because these forces may come from the boundary conditions. Okay, but as I told you, I'll not focus on the boundary condition. So the boundary condition will be replaced by the equivalent forces. So that means A and E can also take some force. All right.
Yes, sir.
Okay.
Yes, it can be.
Yeah. So now, what can be the easiest approach? Can you tell me what can be the easiest approach to go from here to here? Is it a direct approach, which will be easy, or we can go from here to this and then from here to this via SFD, which will be beneficial? Via SFD, right? So this two-step process will be easy. Yeah. So, and we'll take help of some important equations. I don't know whether, I think Professor Sushant Chakraborty, when he discussed this concept of this internal forces, he has mentioned these two important equations. One is the shear force and bending moment relation, and another is the shear force and the uniform, so the load intensity, which is the uniformly distributed load or triangular load. So that is the distributed load over the beam. So this is Q is the distributed load, okay? Applied load. So do you remember these equations?
Yes, sir.
Yes, sir.
Yeah. So this will help us to draw the SFD from the BMD, because you know this relation will be very much helpful. You can see why I am talking. See here. Yeah, in this problem, as I told you, I'll just start from this side. Okay. So I'll start from the right side to the left side, and I'll first focus on this diagram. You can see this Venn diagram is linear, starting from one point, and here it is going to 0. All right. And I know that the slope of this will be equal to the shear force. dm by dx equal to V. And what is the slope?
Negative.
Yeah, the slope is negative. And let us say if you know the distance and if you know the value here, then you can find out what is the slope by taking this height divided by the x position between these 2 points, right? So then you can see the shear force, because the slope is negative, shear force will be negative. That means this, and it will be constant because the slope is constant throughout. Then that means this is the shear force diagram. So I'm just not giving any value, because this is, if you fix some value of this height and this distance, then probably you can find out what is the value. But let us not concentrate on the values first. Just representative diagram we'll try to draw. Okay, so this is what the shear force diagram will look like in between this point. Now come here. So you can see here what is happening. The slope is
Positive.
positive, and it is linear, means constant. That means the slope is constant. That means the shear force will be constant, and it is positive. So that means I have to go suddenly towards the positive x, and you can see this slope is higher, and this slope is like the magnitude of the slope is less compared to this slope. So that's why this shear force will be the distance from the x-axis will be less compared to this distance. Okay, so I'll draw it here. Maybe I'll use the green color to represent these lines. Yeah. So now what about this BC portion?
Sir, slope is negative.
Slope is negative, and
Minus
probably
of
if I have a symmetric M here, then you can see it will be same as this one, right? So it will
Yes,
look
sir.
like, yeah. So it is this.
Yeah.
And then what will be here? It will be just exactly the same magnitude of this, but it will be positive. So it is here. Okay, so this is your shear force diagram. All right. So now you know the shear force diagram. Can you tell me what will be the force diagram, the free body diagram? You can see here, this is magnitude. Now let me just give the value here with F1, F2, F3 maybe. So let us say this one is F1, negative here, and this is F2, and then this is minus F2, and this will be F1, right? So let us just mark this magnitude in this way. So now can you tell me what will be the force? So I'll prefer to start from this side. Okay. So if I start from this side,
reaction at E will be F1.
so at E, what will be the force?
F1.
Upward direction, sir.
F1
F1,
upward.
F1.
F1 upward or
Upward
downward?
direction. Upward.
Yes,
Upward.
upward.
Yes. So that's why this, you can see F1 will be upward. Why? Because if I just take a cut portion here and try to draw the shear force diagram, yeah, I know the sense of the shear force and bending moment, Vx and Mx positive in this way. And then to become Vx negative, I should have a force which is going upward. Then you can see this F1, Vx plus F1 will be 0, and then Vx will be negative. All right. So then you can see if I move from this side, a negative shear force means a upward applied force. Okay. But this will be different when you look from this side. We'll just come to that maybe after finishing the entire loading from this side. We'll come back to the approach from this side, left to right, maybe after finishing this one. All right, so this is, and then magnitude is F1, right? And what will be your D point?
Sir, downward direction.
Minus F1 plus F2.
Yes, you can
Downward
see
F1 plus F2.
this here you have to go up, but it is adding some shear force, right? Because this is actually added. So I was here and then something is added. So addition means the positive shear force. So it will be downward. So positive shear force means you have to give downward force. And this one will be magnitude because this is F2 and this is F1. So it will be F1 plus F2 magnitude. Okay. All right.
So minus F1 plus F2 should be.
Huh? No, this is the total magnitude. No, this is the magnitude of. See, this magnitude is F1, and this magnitude F2. This height is how much?
Yes,
This
sir.
height is F1 plus F2.
Yes, sir.
And this height only you have to put here, right? Do you agree or not?
Yes, sir. Yes.
Yeah. So now come to C. You can see from F2, this line, I am actually going down again. So going down means negative side. So force will be upward, right? Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
Force will be upward. And what will be the magnitude of the force?
2F2.
Yes, it is 2F2. That's correct. And what about the B point? You can see from F2, now again this is F1 plus F2, and it is additive. So you are adding. Additive means you have to put a downward force, and this is F1 and F2. And now you see here, this is F1, and now you tell me what should be this force at A.
Upward
F1
direction.
upward.
yes, it is upward direction, and the magnitude will be
F1.
F1. And if you are confused about this, what should be the direction at this particular extreme point, you can just think of cutting one section here. You'll see if I try to draw the SFD and BMD diagram from the free body diagram approach. So Vx and Mx, this is my positive sign when I take a cut portion here. And this is your point at A. You can see to make this Vx positive, because this is positive here, you can see it will be down, upward. All right. So you can see that now you can look at this difference. If I go from this side, left to right, then you see a upward force is giving a positive shear force. And then you can see this one will, a downward will actually have a negative effect. Like you have to go down by F1 plus F2. And then this is upward, so you have to go up. And then you have to again go down for F1 plus F2. And then this is upward, so you have to go up. All right, then you finish this diagram. Okay, so that's the difference. So if you go from right to left, upward is actually starting with negative, and then you add for downward and subtract for upward. But from here, if you go, you'll see upward is actually additive effect and downward is the subtracting effect. So you just subtract whatever the downward force. If you go from right to left.
Hello, sir.
Left to right. Go ahead.
Sir, going from left to right, it would be easy somewhat, I think.
Yeah. So that's why I told you. No, sorry. No, you are telling that this is easy. So both are fine. So it is actually human perspective, I think. So I think I feel that this because my the x direction is I take this way, left to right. So I somehow feel this right to left is convenient. Okay, because if you
Sir,
see,
right to left,
can you come again?
Right to left, we have to consider upward as a negative, but left to right, we have to consider upward as a positive. That should be easy. Upward as a positive.
No, that is your convenience. No, so that you see why I told you, because when you draw a cantilever beam, how you represent a cantilever beam. So generally we represent a cantilever beam by a support here, right? So
yes,
if you
sir.
see, and then for a cantilever beam, it is always better to go from this side, because even you can draw let us say there is a force P. If I tell you to draw the shear force and maneuver diagram without finding this reaction, you can see I can draw the shear force diagram by taking the cut section and taking this one, not this one. Okay, so that from this particular sense, I feel that going from this side it will be better. But it's actually technically both are fine if you understand the concept clearly. So both are fine. Okay.
Okay, sir.
So no issues. Yeah. Now if you see now coming to the last point. So this particular bending moment diagram is the result of this force. Now if I just ask you to find out a legitimate beam with boundary conditions, so what will be your final beam configuration? So you have to just replace some force by an appropriate boundary condition, right? So what can be the boundary condition? You got my question? So this is my FBD. Now I want a beam configuration. So easiest way is you just replace these two forces
Point.
by one roller support and one pin support. And you will see that if this has to be in equilibrium, then for given loading of this kind, at A the reaction will be F1, and at E the reaction has to come F1 here. Okay, because you can see this is symmetric and all, so you don't have to worry about what is the reaction at this thing. So finally, you can say that this bending moment diagram, whatever we have shown, is a result of beam configuration of a pinned. This is called simply supported beam. So one side pin, another is roller. So it's a simply supported beam where there are three forces applied: this, this, and that. And then you can see the first suggestion one of you gave, that forces on BCD with a boundary condition at A and E is the answer. Okay, that's correct. But if I just look at FBD, then I should say 5 forces, where A and E will have also some forces. All right. So now I will give you one more for your exercise. And I think I saw that some of, like, one student tried for S, but I think there was some issue with that S. So let me give you, or let us discuss that. So there is a diagram of S I want, which will look similar to this. Let us say this is L by 2, this is L, and yeah. So this is your final BMD. And now I want SFD and then the final beam. All right. So can anybody suggest me what should be the SFD? Again, this formula can be of your help.
Select cost function, opposite to this phase change.
Parabolic.
No.
Use parabolic function. It will be easy, I think.
It should be like opposite V.
Opposite?
Inverted V, kind of.
Like triangle. Yes, sir.
Yes, that's correct. Inverted V, but you have to be very specific where it is starting, where it is ending. So
Yes, sir. It will basically cut the x-axis in the midpoints of both the parts.
Yeah, and peak at the midpoint.
and peak at the midpoint. Okay.
Yes, sir.
So it is something like this. Sorry, it's going off. I'm using a tab where it is sometimes it is difficult. Yeah. So something like this, right? Isn't it?
Yes, sir.
Or you are confused a little bit?
I think it's correct.
Yeah, let us understand whether it is correct or not. Let us understand. So first, if you see, I'll start with this direction. This is my preferred direction. Maybe you can start with that side. That's fine. So let us say if I look at this, you can see this Benjamin diagram. Slope is 0 here. So that means the shear force, because slope is 0, that means shear force has to be 0. So something 0 here. All right. So now the slope is slowly going to the negative side. So it is becoming higher and higher in the negative side. And this is, you assume this is parabolic. Okay. So it can be cubic variation also. Then we have like little, the shear force diagram for uniformly distributed load. The shear force diagram is linear and your bending diagram is parabolic. Okay, so this is linear straight line and this is parabolic. But if you have a distributed load which is triangular, then this becomes, I'm giving you the kind of pattern of this curve, but whether it is cubic this way, that way, so that we have to see how it is applied. So then this is actually parabolic. So your SFD, this is SFD and this is BMD. So SFD will become parabolic for triangular load, and your BMD will be cubic. Okay, so some cubic variation. So you see that if it is cubic, then this will be parabolic. So it is little complicated. So we'll assume that this is a parabolic variation. So our calculation will be a little easy. Okay. So when this is parabolic, this is linear. So that means this will be a linear line, and you can see this linear line is slowly, like the slope is maximum here, and then the slope is going to 0 this way. But here the slope, all slope will be negative. Okay, so that means this is the curve. Now you can see in this case, if I go take this section, let me draw like here A, and probably I'll mark it few points for understanding. Maybe the loading is not divided into that many points, but let us just mark it. So now if you see CD portion, in the CD portion, here there is maximum slope and this is positive. And then the slope is going down, like reducing, but still it is remaining positive and it is becoming 0 here. So that is the representation. And now you can see here the slope is same. This is positive and exactly this is negative. Okay. So you can see here, the slope remains same. It is again positive, but it is the slope is positive and it is becoming 0. All right. So here the slope is 0. So from 0, it is slowly increasing and becoming maximum. And then here you can see the slope is 0, and then in this way it is becoming negative, and this is maximum negative. So this is what the shear force diagram. Now you have to tell me what should be the force diagram corresponding to this point. Can you now tell me?
So uniformly distributed force for C up to C downward and
Upward,
from
sorry.
C
From
upward
A to C
and
upward.
C downward.
No, first let us see again. If I prefer to go from this side. So CDE. Do you want to mention here between CD or DE? From C to E, right side. Upward or downward?
Distributed force. Downward.
Downward.
So I can see some upward and downward. Can you tell me what should be?
Sir, downward should be.
So that means this, right?
No, sir.
Yes, sir.
Is it?
Yes, sir.
Yes, sir.
Why you say that?
Sir, because we noticed that for uniformly distributed downward force, we get a bending moment diagram parabolic upward.
Yeah, that is also one way you can say. But you can see, if you remember this formula, I told you that this is the formula where Q is assumed positive downward. Okay, so this is your Q. All right. So if this is like there is a beam and some load intensity Q downward, this is Qx. It can be any variation. So then dV by dx will be minus of Q. So now you can see dV by dx is negative, right? So
Yes,
this is negative, so that means this has to be positive. All right. So anything else now? What else in this loading diagram? Is this only load C to E or anything else?
A to C upward.
A to C upward. So I can show like this. So anything else?
No, sir.
Are you sure?
Sir, force in at point C, sir.
Force at point C.
Yes, sir.
Moment. No, sir, it is correct because at the changing
Pin
point,
joint at joint at A and roller joint at E.
Yes, sir. At end point, we have to consider some force.
At E and A, right?
Yes, sir.
Why?
Because in shear force diagram, we are seeing that some force is there.
Yes. So you see here, because this is not a zero. So if you look at, if you see, if I have only this, then if I take a small portion, the shear force will become zero, because you see this for small portion, this can be treated as small, so neglected. So this Vx will then become zero, because this load as x tends to zero, this is nothing. So if I have this, then the diagram should have started like this. Okay. So it would have been like this. Starting from zero, it will go to this value. But because it has started from negative, so you have to have some force. Now you tell me which direction the force would be.
Upward.
Yeah, because this is from right side. If I look, it is negative, so it is upward. So there is some force here. The same way, there will be some force here, downward, because this is here negative. Now, if you see, because this is S, right? So if you look from top or like from bottom up or top down, it should be like this is anti-symmetric kind of thing. So the loading also is kind of an anti-symmetric loading. You know, this bending moment, if it is anti-symmetric, then the loading will also become anti-symmetric. If if the bending moment is symmetric, you can see here, this is a symmetric bending moment for M. So the loading has become also symmetric. You can see that. Okay. So, but whereas your shear force will be anti-symmetric. If bending moment symmetric, shear force will be anti-symmetric from this middle line. Okay. And here you can see the loading is anti-symmetric, shear force is symmetric, and then bending moment is anti-symmetric. Okay. So this way you can now you can see if I can replace this forces by equivalent boundary condition. You can put a roller support here and a pin joint at A. So that way it can actually. So the loading can be something like this. So you can see I have a roller support here, and then I will have this. and there is some load from bottom to top. And here I'll use pin. So pin means both X and Y it is restricted, okay? All right, so maybe you can show like this. Yeah. Show this way. Is this fine?
Yes, sir.
Yes, sir.
Yeah. So this way you can try to draw other possible diagrams. So if I have some time, maybe I can just discuss this one more. So one thing let me ask you. So how many of you? So let us say for this particular exercise, whatever we have done is we have started from here and gone up. You can see I have bending moment diagram first, then shear force diagram, then the free body diagram, and then the beam configuration, the actual problem statement. So now if I try to do this approach, so from problem statement to BMD. So now will you be able to solve this problem easily or not? Because
Yes,
maybe this is the forward problem. So in exam, maybe the forward problem will be coming. Okay, this is the inverse problem, you can say. In your exam, mainly this forward problem will be there. So if you like inverse problem, if you are able to solve, then forward problem, I think it will be easy for you. The forward problem is kind of simple. You can see, you can start from here, then you go down up to this, and then this is linear. So go up with, and this is the negative slope. So you find, and let us say if you are confused with what is the value to find out, because you know the load, the reaction you have already found out. So first step is you draw the free body diagram. So find the forces here, and then if you are confused with what should be the value, you just take, you just cut here and take the like moment about this point of this forces, right side forces. You can see there is a force here, there is a upward force for the reaction E. Then you can find out. So this load, total load times the distance, half of this distance. And then this E force times the distance to that force, and you have to take the sense clockwise, anti-clockwise, you will find this point. So directly you can find this point to locate this point, and you know from this force what is this point, and then draw the straight line. So this is the complete diagram of this one. And then you know this force, so you show here and that. So you can see only finding a moment about this point, I can draw the SFD, right? Similarly, if you know this SFD, now it is always easy to look at the SFD, and if there is no applied bending moment in this, no applied bending moment, then you can from SFD you can draw the BMD easily. Okay.
Excuse me, sir.
Yeah.
For SFD, that vertex point, if it is on the x-axis, that vertex point SFD value is 0, then how we will do?
No, this is.
How will the FBD look?
Okay, you are telling something of this sort, right? Okay, let me see that. So you are telling your this thing is something like this, huh?
Yes, sir.
This is your SFD.
Yes, sir. Is this feasible? If we can get in situation.
Let me see. So we'll see that there will be some force here. So you start with the force. and then a distributed load here, right? It will, so you will have a higher force here, and then this you have reached here, and then probably just let me see. You're coming to 0. Because it has to satisfy the equilibrium condition. So if I have this thing, so the shear force is 0 here, right? That is possible.
Yes, sir.
That is possible. Yeah. So then what will happen? You have just 1 minute. So because I'm not giving you the forces and all, so see, the shear force is 0 means if I cut here, so now I have a doubt about this, our previous problem, the bounding. Okay, let me just first discuss this. So shear force is 0 means if I just take a cut section here, then what it just means that this force equivalent, so let us say this is W and this is L by 2. So this is W into L by 2, right? Total force. And this is my Vx and this is Mx. And here I have one load. So this Vx will be 0 only when this is WL by 2. Right?
Yes, sir. Right.
Yes, sir.
So that means if this is WL by 2, then it is fine. So now, and then I can have this, and then again here, there will be, so this is WL by 2, and this is WL by 2. For this kind of loading, I have this shear force diagram. Now the question comes whether this can be a feasible beam loading with boundary condition. So that we have to see. So now you can see the force balance of this one is not happening because you can see, no, I think it's happening, right? Because you have a total force here
Yes, sir.
as
If let's have same
it's
uniform
happening,
loading,
right?
then it will be. Yes, sir.
Yeah. So now, what about this? That's why I told maybe now we have to look back here. So this is your here there is a shear force. That means this shear force is due to this loading, right? For this case, your this one E loading has to be higher than this one, right? So let me see what I'm speaking. Higher maybe or lower, I don't know. Let me see that. So this is
Sir,
your
in my case, moment is not balanced.
your case
For
moment is not balanced.
Yes, sir. Omega L by 4 should be force at end point.
Yeah. So
This is not feasible.
no, you can see with some changes you could do it. Okay. So maybe you have to just shift the card a little bit up and down or something. So you can see that it is also possible that it may not be a feasible diagram. So we have to just see that. Okay, let us see. Maybe there is some applied moment or something will come. I don't know. Okay, so let us see now from this shear force diagram. If I try to draw the moment diagram, what will happen? So moment diagram will happen like this. You can see here there is a moment 0 at this particular point, the moment this slope will be 0, right? So it will be, see this let us see here. This is all negative, right? And
Yes,
all negative. And here it is going, so if I come from here, there was some, this thing is negative, and it is becoming 0 here, and it is higher here. That means it will be something like this. Isn't it? And then this is, no, shear force ulta. So it will be like this. Is this the bending moment diagram? Sorry.
sir, the left side is slope is positive in shear force diagram, but you have
Sir,
taken in bending moment
it's
diagram.
just opposite of it.
Slope. Yes, sir.
I maybe
Inverted.
yeah. So here there is slope positive, right? Yeah. So that means
yes,
slope is positive means bending moment will be positive.
Upward, sir. Yes.
And here there is the maximum slope, right? See this, let me just write down. dm by dx is v. And here v is negative and maximum. So that means the slope will be negative and maximum, right?
Slope is positive, sir.
No, this is the shear force diagram, na?
Yes, sir.
So this is v, and you can see v is negative, na, here.
Yes, sir.
So v is negative and high value, and this is the slope. So that means slope will be negative with a higher value, right? And then if I go this way, the slope will still become negative, and it will reduce to 0. So is this not the Venn diagram?
So the right part will be inverted. Again the slope will start decreasing.
Yeah, here the slope will be negative.
Yes.
Sorry, 0, and then?
And then again negative, more and more negative.
More and more negative. So how it will look like?
So there will be discontinuity at may point.
There will be discontinuity, no? Yeah, here it will be same as this one. So yeah, so there can be some discontinuity. Maybe it will start here like this, right?
Yes, sir. It's correct.
So then you can see there has to be some jump, and there is a applied moment, and this is positive moment, and I have to have something like this. The loading diagram will have some moment like this, isn't it? Now, can you see whether it is possible or not? And then you can see for that, this one, there can be some loading of extra load may come. You have to see that. But this is your, I think, total. You have to see what moment, maybe M0, and then by taking force balance, you will see what can be the relation between this M0 and this W. You can find out. I think this is fine, no?
Yes, sir.
Yes.
Look at this problem. Maybe we are trying to solve it very quickly. Look at this problem. I think it can be done, but you have to have some extra moment or something applied. So you just look into it carefully. Probably you'll be able to find out. Okay. All right. I think we have done quite a bit on SFD and BMD. So one important thing I'll just try to mention here. So sometimes people make mistake. So many times we say that if there is a distributed load, for example, if I just tell you that this is the beam load, okay, and this is cantilever beam, let us say, and this is W0 per unit length, and let us say this is L. So now, many times we say that you convert it this UDL to equivalent force and try to find the reactance and all. Okay, so then we do this W0L at the distance L by 2, and then you see find this BX MX. Sorry, BA, let us say this is A and this is B, PN and MA.
Sir, MX should be in opposite direction, sir. Sir, MA should be in opposite direction.
No, that is fine. That will come negative because our convention, you just put it. Because our load sign convention is this side it is this positive and this way, and this side it is shear force this and this, right? So it may come negative. So if it is negative, it implies that MA should be reversed. Okay, but you saw this way. This is consistent way of doing this. Okay. Right, so MA may come negative from your calculation equilibrium equation. That's fine. So now my point is, so then I can find what is MA. It will like VA, we will see that it will be W0L, and MA will come as W0 L by 2, L square by 2, and negative signs. Right. So now if I tell you that solve for SFD and BMD of this particular problem. So this problem, find the SFD and BMD. And one or two students, because sometimes we say this thing that this is equivalent. Okay, so they just take this one and start drawing the SFD and BMD of this problem. What will be the SFD BMD of this problem? You can see SFD will be here. There is some load coming like this. So this is your W0L, and the moment equilibrium will say. You just verify. You will see that it will be 0. It will be coming here. So this is W0 L square by 2. So this is BMD and this is SFD. But do you think that these are correct solution? What is your?
No, sir.
No, sir.
Why not? What is wrong here?
Sir, here force will be distributed for that section at a different point in BMD.
Yes.
If you consider section wise.
Yeah. So then what is the issue with this equivalence? So is it not equivalent?
So it is equivalent. We can use that to find our MA and force, reaction force.
Yeah,
Yes.
so that's the catch. This is equivalent. You can write this is equivalent in a given FBD. So you draw first the FBD, and after drawing the FBD, you replace that distributed load with the equivalent single force or point force. But it is not the equivalent of the loading. Okay, this is not equivalent. If I try to, what is equivalent then? This is not equivalent. What is equivalent? Now, if I try to draw a FBD of the entire beam like this, VA and MA, then this is equivalent to having this. Okay. Or simply, if you see, this is one, and another way you can see if I cut a section like this, then if I have a portion, like the right side portion, if I take W0 and let us say this is L minus X. Okay, I have cut here at X. Okay. And then this is my Vx and this is Mx. Then this is my FBD. Once I have FBD, then I can draw one equivalent of that by drawing one force here. Sorry, this is Vx, this is Mx, and this is W into L minus X at this distance, which is L minus X by 2. So this is equivalent. So once like you are in a free body, then you say that this is equivalent. But these two are not equivalent. This is not a free body, so this is not equivalent. You understand? So these two are not equivalent. So if somebody is doing this way, so this is incorrect. All right, so sometimes we have seen that people are making some mistake in this kind. So please make a note of it, okay? All right, so now the class is open to take one or two questions. And if you have some doubt regarding this SFD and BMD, please ask.
Excuse me, sir.
Yeah, go ahead.
Sir, in this question where you said that it is not like equivalent, sir, so equivalent can only be used to find the reactions, right?
No, equivalent reactions means yes, this is internal reactions. So not only external reaction, you see this is external reaction, right? VA and
Yes.
MA. You can find VA and MA with an equivalent where this is like equivalent of the entire thing. So W0 into L at L by 2 to find this MA and VA. And here I am using equivalent. This is also equivalent. But I am using that equivalence for finding internal reactions. What I am telling, this is a legitimate free body diagram, right?
Yes, sir.
So this is, you see this green colored box. So this is a legitimate free body diagram of a cut portion which is taken right side of the cut portion here. So once I have a free body diagram, within this free body diagram, I can replace this by one equivalent force. And that is what I am doing. I am taking W into the distance, total force is W into the distance L minus X and acting at the middle. Okay, so you can do equivalence within a free body. That's what I am telling. If you have a free body diagram, a legitimate free body diagram, After that, within the free body diagram, you can just remove this and put it equivalent force. But that if this is not a free body, so this is not a free body diagram. I cannot replace this with a single force because altogether that will be a different problem. Understand?
Yes, sir. Yes, sir. Understood. Thank you, sir.
Yeah.
So actually, sir.
Yeah.
First, we have to make the body free, and then we can take uniformly distributed load as a concentrated load at its center of gravity.
Yes, you can. If you put it that way, also fine. Because body free means you are drawing actually the free body diagram, right?
Okay, sir.
Yeah. So after drawing the free body diagram, you are making the body free from surroundings, and that's why you are you have to put equivalent like the reaction forces at the external supports where from you are removing that particular component. Once you are doing that, and then you have a free body diagram. After that, you can make this uniformly distributed load as equivalent point force by putting a resultant force acting at the centroid of the area. Okay, so here for rectangular load it is at the middle, but you know if you have triangular load, then it is at the centroid. So if you have some load like this, let us say this is the load, then the equivalent force will be the total weight. So if this is W0 at the end, and this is L, let us say this is a cantilever beam with some uniformly distributed, sorry, a triangular variation. This is a triangular variation. And then the equivalent of this is W0 into L by 2. You can see it is half times the base times the height. And then it is acting at the centroid. And that means this distance is L by 3. And this is 2L by 3. So it happens for triangular load. Okay. And for uniformly distributed load, it is at the middle. All right, so I think we have almost taken like 2 hours, and you may have classes up to that. So, and I think you have exam on 11th. Yeah, go ahead.
So this week, shall we have assignment?
I think most probably it's not, okay, because you have exam coming next week. So I think it will be, let me see the date. And I think you have exam up to 12, right?
Yes, sir.
Yeah, so 12 is Friday. So I think like I have to discuss with the other faculty. Maybe I just forgot. We had a discussion, I think, but I don't want to just give you 100% correct answer right now. But I feel that it will be on next week, not this week, because of your exam. It will be given on 12th. Okay. So if I'll post it, Professor Jain, Atul Jain is out of station, so I'll get all the information from the coordinator and the other faculty member. Then I will post it in your MS Teams chat box. Okay. So most probably it is not, but I'm not 100% sure. Maybe 98% sure about that. Okay. Yeah. So you have a mechanics exam on 11th, and most probably after that you will have this assignment based on topic 6. Okay, but your 11th test will be on the 3 topics: topic 4, topic 5, and topic 6. So trusses and frames, frictions, and that internal forces. Okay. Yeah, so I'll post it very quickly. Okay, so you'll get that information from your MS Teams chat box. All right, so thank you for attending this class. So I'll stop the recording now. And then